Okay, so the goal of this activity is to produce a proof of this pattern that we kind of already spotted. Okay, so we're assuming the pattern, you know, and so the rule is there's a tick in like a certain square if in the 3 squares above it there's exactly 1 tick. Okay, and if we follow this pattern, it kind of starts at the top and gets this kind of pattern where it's like 1, 3, 3. Okay, and the question asks you how many ticks are in the 128th row, right? So if you kind of look at the pattern, you'll see that, you know, the first row has 1 tick, the second row has 3 ticks, right? And then it kind of repeats over here, yeah. So that the fifth row is the fourth row is basically double the second row, right? And then you keep going down. By the time you get to the 5, 6, 7, 8th row, right? It's again double the fourth row, right? So every power of 2 is double the amount in the previous power of 2. Okay? And it's a multiple of 3, you know? So then you actually know in the 128th row, which is 2 to the 7, right? There should be 2 to the 6 times 3 ticks in the row. Okay? Okay. So the thing that I think will get most people if they were trying this in the exam is that if you were to make it's kind of clear you should do this by mathematical induction, right?
Yeah.
Okay. But sort of the skill in mathematical induction comes from the statement you choose to induct on, and not necessarily sort of how the proof goes. And so the problem with choosing like this as your statement to induct on, so in general, the problem is like if the statement's too weak, then you don't have enough to prove the induction step, right? And if the statement's too strong, you can't prove it in the induction step. Okay. And so we want like a statement that's just right. So just saying the number of ticks in the powers of 2 row is just not enough. Okay. So what I propose is we make the statement something like this. So first you single out a row, right? And you can label the things in the row like 0, 1, 2, and then -1, -2, -3, yeah? Okay. And so instead of stating that there's, 2 to the like essentially 2 to the like m minus 1 times 3, right? We say not just that, but exactly where they are. Okay? So basically say that like there's nothing in place 0, there's something in place 1, 2, 3, there's nothing in place 4, right? So another way of saying that is that there's a tick anytime that it's not a multiple of 4.
Yeah.
Right? And then we can also like name the extremity, yeah? So we just name these 2 squares where there's the last gap. So the last multiple of 4. So in this case, what is this? Huh? So here there's like 4. It's like 8, right? There's 2 multiples of 4. So it's really how many groups of 3 there are, right? So if there's 2 to the m minus 1 groups of 3, then the sort of the square that is right outside the last ticks should be you know 2 to the m plus 1. Wait, 2 to the, was it this number times 4? Sounds a bit big, but Okay. Yeah. So 2 to the m plus 1 on either side, and minus 2 to the m minus plus 1. Okay. Yeah. So the advantage of that is, so now you know how to go from there to the next row, right? Because if you just knew the number, you didn't know where they were. You don't really know where to go from there. You know what I mean? So the statement was too weak before, and this is fine because it's stronger, but you can actually prove that, right? So it's actually better. So okay, and then so how do you achieve the induction? Well, you got to do the base case. So you just do like, on the the first row, the second row, the fourth row, it's all correct. Yeah. Okay. So then the induction step is you assume it works on the 2 to the mth row, right? And you want to prove that it works for the 2 to the m plus 1 row, right? Okay. So, but now your induction hypothesis has enough information for you to calculate what to do, right? So, so if that's your, if that's your induction hypothesis, that the details of that row, right? Then from the rule that you have, you can deduce that the next row has exactly 2 things at the ends, right? Okay. Not only do you deduce that it has 2 things at the ends, you actually know exactly where those ends are, right? Okay, so you can deduce that the next row, so the 2 to the m plus 1, the next row, it has ticks exactly at the so it's just 1 over. So it's exactly this 2 to the m plus 1 and minus 2 to the m plus 1 place, right? That makes sense, and it's all empty everywhere else. Yeah. Okay. So by your induction hypothesis now, so this is the crazy use of the induction hypothesis. Because effectively what you're doing is you got a bunch of ticks, right? You calculated one further and you just got one tick on each side, right?
Yeah.
And what you can do with your induction hypothesis is say that relative to this tick, 2 to the m rows down from that, you get the pattern that, you know what I'm saying? You get the pattern that you had for the 2 to the mth row, right? Okay. So for that to basically work, um, so for that to basically work, you need to show that that cannot interact with that, right? Okay. So I guess the only chance any of it really has to interact.
Can you say the length and how that correlates to the width?
Yeah, so I mean we know that the column in here is the 0 position, right? And um and we know that this occurs in 2 to the m plus 1. And we know that this goes exactly back to 0 here, right? Because that's 2 to the m plus 1 across. Yeah?
Yeah.
Okay. And so for them to interact, okay.
What I did was I just said the bottom of whatever triangle you started with, it's like copied and copied, and there's a gap in between. And because of the starting point, it has to be like 3s.
Yeah, but the point is, yeah, like anything on the right side of this 0 cannot be influenced because it's only influenced by these 3 squares, right? So the two halves legitimately don't interact. Okay, because the only thing.
When they interact is when it breaks.
Yeah, on the next row, yeah. Yeah, up to that row, the furthest thing it got to the other side was where it got to the middle. which we know is empty. Yeah. Okay. Okay. So can you see how that proves the question? So the induction hypothesis is used to show. So the inductions, the statement is to show exactly what goes on the 2 to the mth row, right? Relative to having a tick at the top. And then you use that to get that there's 2 ticks at the outsides, and then you use the induction hypothesis to get that row 2 to the m down from there, right? And so if this is 2 to the m down from 2 to the m row, then it's up to the 2 to the m plus 1, right? And so the 2 to the m plus 1, it looks exactly like what we claimed it should look like. Yeah, it's missing every multiple of 4 all the way up to the thing.
Yeah.
All right.